Jim will be discussing cruising the summer Milky Way, a Galactic perspective, and it should be a really good talk. He has been a visual observer and is currently working on 6 Astro League observing programs. And he loves to observe with a small, simple telescope, but has been known to take on the Messier list with a 4-inch mini Dob. And he's been a member of the RAC since 2017. And so, Jim, go ahead and take it away.
Thanks, Ann. I can't share because you're still sharing. So if you can,
I'm sorry. I'm going to unshare.
You're
okay.
good.
Let's see. Can I? Oh, here it is. Here it is. Okay. You're good.
All right, perfect. See if we can make this work. All right, everyone, you should be seeing my full screen presentation, correct?
Yes.
We're good. Okay, thanks everyone for coming out tonight. In the chat, I'm placing a link to a Google folder. You can feel free to go now. You can go later. I'll also have a QR code if people are interested in downloading the observing list that we'll be talking about tonight. It's there as a CSV file, also as a Sky Safari observing list. So you can feel free to check that out if you'd like to.
Okay.
So tonight, I'm going to talk to you all about observing the Milky Way and what we can understand about where we are. So tonight's topic is, that's right, summer nights. So I got my first real telescope during the summer and several summers ago. And I spent all summer trying to find and observe the very best objects up and down the Milky Way. And I was not at all successful in doing this. Some of you might be able to relate to this. I had a shaky mount. I had a bad finder scope. I had no real expectation of what I would see or what I should even be looking at. Still, it was a summer of just fascinating discovery. If I came back in after finding just one Messier object, the night was a success for me. So over time, I got better at finding objects and seeing them, which of course are not the same thing. But then, as we often do, I wanted to understand more. When I first started out in astronomy, it was recommended that I think about the night sky as ancient civilizations did. Think about it as a giant sphere rotating around the Earth. And it turns out, if you think about the Earth as the sky as a giant sphere, that works quite well. You get to understand the motion of the seasons. You get to understand the positioning of constellations. But what it doesn't do is help you understand sort of where we are in the night sky. And so that's the part that I wanted to know more about. So I stumbled across this book in the library. I don't know if any of you have seen this, Binocular Astronomy by Crossan and Tyrion. There's a chapter in this book that talks about a galactic perspective and how you can actually stand under the night sky and begin to understand the structure of our galaxy. So Crossan and Tyrion point out the fact that if you had no prior knowledge, you would probably never intuit how the night sky maps onto galactic structure. So ancient people, for example, that's why they created the sphere, because that's what you can perceive. But we're not starting from zero, right? We have centuries or decades of scientific knowledge behind us, detailed measurements to distances of many celestial objects, etc., that we can apply that knowledge to what we're seeing and gain a deeper appreciation for what we're observing and our place in the galaxy. So I looked it up a couple of weeks ago. If anyone's interested in buying this book, it's currently on sale for $987.25. I bought my copy for $7.50 4 or 5 years ago. So I recommend getting this from the library, perhaps, although you'll note this is the really rare 1696 edition on Amazon. But this book and this chapter led me to other resources, books, articles, software, a lot of which I'll share with you tonight, to better understand how we can observe galactic structure from our own driveways. This structure is visible, a lot of it with your naked eyes, from even moderately dark skies like big woods, if we know what to look for. So the goals of tonight's talk are twofold. So one, I want to lead you on a cruise through the summer Milky Way. If you're maybe new to astronomy or you're just looking for some stuff to look at this summer, we're going to look at 30 objects that look great in almost any telescope. And almost all of them, maybe all of them, are at least visible in binoculars. So lots of these objects are easy to find and easy to see. Some are more challenging, especially under light polluted skies or with a smaller scope. So if you're not sure what to look at this summer, this list is going to be a great start. And again, in the chat, there's the link to the observing list. If you want to download it and load it up into Sky Safari, you can follow along. You can check that out later. So many people, of course, right here in this meeting would include additional objects to sort of the summer's best. But I think these 30 objects would be on most people's lists. This list represents all major deep space object categories with the exception of galaxies. And galaxies for a very good reason that we'll talk about. We're looking into the Milky Way. We're not going to see any galaxies other than the Milky Way. Mike, the book was Binocular Astronomy. Right there. There is a second edition. There's some controversy about that. You can check out Cloudy Nights for more info on that. But this edition is great and normally selling for much cheaper than $987. So second, and very importantly, along the way of this tour, we'll see how the structure of the galaxy is evident in what we're seeing, giving us somewhat of that galactic perspective. So what's the Milky Way like, and how do we fit into it, and how in the world do we know? Well, unfortunately, we can't get outside of our galaxy to get a better view, right? But fortunately, we don't have to. First of all, we see other galaxies and can assume that our galaxy is in some ways similar to other galaxies. We also have distance measurements to different objects. The distribution of objects in the night sky, where objects cluster, as well as images of our own galaxy in different wavelengths that cut through all the intervening gas and dust that have enabled astronomers and astrophysicists to arrive at a fairly detailed understanding of the galaxy's structure, at least in our local area. New information, of course, is coming in all the time, right? In fact, earlier this month, NASA released a highly detailed image of the galactic core made of more than 20 years worth of data. So I haven't even attempted to keep up with the latest science on this for this talk, because what we're doing is we're not taking sort of the latest and greatest scientific knowledge of this. We're looking at it from an observer's perspective and what we can observe with our own eyes and our own tools. So Mark Matthews has the comment there. Exactly. We know the Milky Way is a spiral galaxy, likely with a small central bar and a moderate sized bulge. So it probably looks something like M51, the Whirlpool Galaxy. Not exactly, but probably something like this, right? If we could get above the galaxy. Of course, the problem is that we're in the galaxy, right? We see our galaxy, though, edge on, right? Just like NGC 4565 or the Needle Galaxy. So here we can see a central dust lane. We can see the bulge in the middle. And the combined light of billions of stars stretched out across a relatively thin galactic disk. We got to remember that much like the rings of Saturn, galaxies are very thin. The halo of a galaxy is very thin relative to the size of the galaxy, right? So we see our galaxy edge on, but really up close, right? So imagine the Needle Galaxy. Sorry, jump there, but up really close. So that's the first step in understanding the structure of our galaxy, as we can observe from our driveways, that we're seeing our own galaxy edge on from relatively close up from within the disk, okay? So again, when I say relatively close, the Needle Galaxy is about 39 million light years away, whereas we're only 30,000 light years or so from the center bulge of our galaxy, nothing in the scheme of things, right? So we're seeing our own galaxy very close up, edge on from within the disk. So when we look across the Milky Way, the summer Milky Way, right, you'll see here, you'll see Cygnus on down to Sagittarius. You'll see the Great Rift. The Great Rift, of course, is just a dust lane, like we would observe in many of the galaxies we can see in our own telescopes. The amount of dust and gas in the galaxy blocks a really large amount of our view, meaning we can only see so far in visible light, which is, of course, what we're interested in from our driveways. Fortunately, though, we have a number of windows where the gas and dust are really thin, or relatively thin, and we can see through to other parts of the galaxy. So in our tour tonight, we're going to be taking advantage of some of those windows as we move through. So this map changes all the time. I'm not even sure how updated this particular map is, but that's okay. For our purposes, it's going to work just fine. We know that we are located in what's sometimes called the Orion Spur. There's some research that says, no, we're a full-on arm. But whatever this is, we're in this Orion arm or local arm. Approximately 28,000 light years from the galactic center, although some studies say the galaxy is much bigger, but this will work for now. And the galaxy itself, we think, measures about 100,000 light years across, give or take. Depends on the study you read. So as we'll see in a few minutes, distance measurements suggest that we lie towards the inside of our own particular local arm. So if we look towards the galactic hub, there are relatively few objects in our own arm compared to looking outwards towards the galaxy. We'll see that in a moment. So almost all of the objects we can see in the night sky, with two exceptions, almost all of the objects we can see are found in the local arm, the Orion arm, further out from us in the Perseus arm, or closer in the Sagittarius arm. Sorry, right here, I've jumped an arm there, the Sagittarius arm. The two exceptions, of course, are globular clusters, which are found in a halo around the galaxy and not so much in the disk, and galaxies, which of course are everywhere we look, although they cluster as well. We know the Virgo cluster, sort of thing. But essentially, our view in this particular direction this summer is blocked by the Milky Way. So that's why spring is galaxy season, because we're not looking directly into the Milky Way and we're able to peer out past our own galaxy. So we'll also see one case where we can see the galactic bulge, the furthest object we can see with our naked eye in our own galaxy. Okay, in the own galaxy. The Andromeda galaxy is, I think, the furthest thing we can see with the naked eye, but within our own galaxy. So going to take you on a little trip. You can close your eyes if you want to. No judgment here. Don't feel pressured. You can imagine yourself on a warm summer night. The sun has recently set. The sky is growing dark. There are no mosquitoes. There are no street lights. Your neighbor doesn't have their porch light on. You're facing east. South is to your right. And so the view from our driveways or big woods might be something like this. Right? We can clearly make out the summer triangle here. We have Vega, Deneb, and Altair forming the summer triangle. Cassiopeia is rising very low in the northeast, and Scorpius is arcing up pretty high over the southeast. This was created in Sky Safari, and I think it is for 9:45 p.m. tonight, which is when twilight ends, over the first level of twilight ends. So this might be what it looks like for us from big woods or from our driveways. Now let's imagine we're under even darker skies, right? We can clearly trace the route of the Milky Way from Cassiopeia up through Cygnus and down through Scutum and Sagittarius. This is the route we'll be traveling on our tour of the Milky Way tonight. And all of this is visible from my own particular driveway on a summer night, although of course I have to imagine the Milky Way part. I'm sure no one's seen the Milky Way from my part of Wake County in a couple of decades. Now, here we can see that some of the constellations lie above or below the disk, right? And this seems obvious at first, but if we're thinking about this in 2D space, it doesn't tell us much. But if we're thinking about this in 3D terms, it tells us a lot. Remember, we're seeing the Milky Way edge on from inside the galaxy. What that means is we can look up out of the disk and we can look down out of the disk or straight into the disk as well. So Vega and most of the objects in Lyra are above the galactic disk relative to us. And the constellation Delphinus, for example, lies completely below the disk of the galaxy. So again, imagine you're standing on this very thin disk. You can look inwards, you can look up, you can look down, okay? That's the second step in understanding where we are and what we're seeing, that we're literally seeing objects above and below the disk of the galaxy, okay? So these are the objects that we'll see on tonight's Milky Way cruise. Some technically aren't Milky Way objects, right? Like the Ring Nebula in Lyra, but it's just too good to pass up. You gotta catch it when you're going by it. But we can also notice something else here. We can notice something important about how the objects are distributed across the night sky. Okay, first of all, most of the objects lie in the direction of Sagittarius. That's clue number one, that there's more galaxy in that direction than in the other directions. And of course, Sagittarius lies in the direction of the center of the galaxy. As we're going to see at the end of this talk, in that direction, we're seeing at least 4 different levels of galactic structure. Think about peeling back an onion. There are at least 4 levels of peel in that direction. Second, we can see that there are 2 big gaps in the distribution of objects. One between Cassiopeia, or sort of the bottoms of Cepheus here, and Cygnus. There's really just not a lot going on here, right? As well as between Cygnus and Scutum. So basically the territory here around Aquila. As we're going to see, these 2 gaps represent space between our galactic arms. So when we look at Cassiopeia, we are looking outward. We're going to see this in detail in a minute. We're looking out of our galaxy, away from the center of our galaxy, to the next arm out, the Perseus arm. As we sweep our view across the Perseus arm, we get to the inter-arm space, the space between the arms, where there's just not a lot going on. And we see that reflected here in the relative lack of objects. As we're looking at Cygnus, we're looking straight down our own local arm. In fact, we're rotating in the direction of Cygnus. Cygnus is ahead of us by however many light years in our rotation around the galaxy. So we're looking straight down our arm here. But again, as our view turns, right, as we turn, we are going to cross the inter-arm space between the local arm and the Sagittarius arm, where there are relatively few objects. That is what's going on here in Aquila. So again, almost all of what we see, with the exception of globulars and galaxies, are in one of these 3 arms: the Perseus arm, the local arm, the Sagittarius arm. Okay? Now, just so you don't think that those inner arm gaps, that distribution showing the inner arm gaps, is an artifact of the particular objects I happen to choose for tonight. This is the Astra League's Open Cluster Observing Program list for this time of year, for tonight, showing objects that show the same basic pattern, right? It's not quite as sparse as my list was, but we still see there's a big concentration in Cepheus and Cassiopeia. It thins out between Cepheus and Cygnus. That's that inter-arm space. A big concentration towards Cygnus, looking down our own arm. It thins out again, right? Even on this list, there's not a ton going on around Aquila. And then it picks up again as we move towards the inner Sagittarius arm. It's also really clear how open clusters in particular are distributed along the band of the Milky Way, with very few examples above or below. So to look for open clusters, you're going to be looking straight out into the disk, not above, not below. So this is another view from the top, but this is from Sky Safari. So showing what we just saw, I'm just going to go through that again, just to make sure we're all oriented. So as we look towards Perseus and Cassiopeia, we are looking out towards an arm that's out from us, the Perseus arm, right? As we approach the edge of Cassiopeia into Cepheus, we're entering this inner arm space where there's just not a ton going on, at least not for small telescopes. There are, of course, objects in these directions, but they're all pretty far away and pretty dim compared to sort of these showpiece objects that we're looking at, right? As we move through Cepheus, we enter some blank space in the far, what would that be, north of Cygnus? I think that's probably north of Cygnus, until we hit the big cluster where we're looking straight down our arm, okay? Looking straight down our arm towards Cygnus. As we approach the edge of Cygnus, we enter into Aquila, where we're not seeing a whole lot because we're in inner arm space. As we approach the tail of Aquila, I'm pretty sure that's the tail. I think he's flying south to north, right? As we approach the tail, we start to get some more objects again as we pick up Scutum and Sagittarius and part of Scorpius as we move in that direction. So again, this is what we're going to be doing, just rotating right around the sky in this direction. Now, what we're going to see too, as we go through these objects, is we're going to pay close attention to the distances, right? So essentially, these arms are, 3,000 to 4,000 light years across, give or take, generally speaking, right? So what we're going to see is if we look in the direction of Cassiopeia or Perseus, and we see something that's 6,000 light years off, that has to be in the next arm out. In fact, that's how the structure of the galaxy was first discovered. astronomers realized that objects clustered at certain distances with very little in between them. All right. If we look 5,000 or 6,000 light years towards the center of the galaxy, again, we have to be in another arm. Okay, there's no way around it. Now we can look quite far in this direction in our own arm because we're looking straight down the arm, right? But if we're looking away from our own arm, we're going to see that those distances become really, really important. If we look the other direction, maybe this will be a talk again in December. If we look towards Orion and Gemini, which is the winter Milky Way, almost everything we see in that direction is in our local arm. This again tells us that we have to be on the inside edge of our own local arm. If we look out this direction, we clearly and easily see the next arm. There's not a lot of our arm blocking the way in between. If we look the opposite direction, we really don't see the Perseus arm in this direction. We're only seeing our own arm because there's all of this bulk of our arm line in that direction. What that means is when we can see the Perseus arm in Perseus or Cassiopeia, we're looking through a window through the gas and the dust. One over here that allows us to see this outer arm, and one this way that will allow us to see all the way to the galactic bulge in Sagittarius. We'll see more about that in a few minutes. Okay, let's begin our cruise down the Milky Way. I'm going to present 30 objects. I'm not going to talk a lot about any of them. I'm just going to give a few little tidbits and why they're important to helping us understand where we are in the galaxy. But again, if you're looking for something to observe tonight, although I think it's maybe still raining, if you're looking for something great to observe tomorrow, you could do much worse than this list of objects. Okay, we're going to start to the left as we're facing east. We're going to start towards the north, looking out to the Perseus arm, right? So I've got Cassiopeia here. The double cluster, which we're going to talk about, is technically in Perseus. Perseus isn't going to be fully up for a while, but sure enough, I spotted Cassiopeia, no problem, the other night. So we're going to start looking out. In this view from Sky Safari, you can see that we're looking at NGC 869, which is the double cluster, 869, 884, the double cluster, at a distance of about 7,000 light years. Remember, our own arms are 3,000 to 4,000 years. So we're clearly outside of our arm at this point, right? So looking out that direction through that window of space. So the double cluster, if you haven't seen it, please go see it. It's going to be much easier to see in the fall than it is right now, but if you stay up late enough, you'll catch it. And all of the sort of the background information I've pulled out of I've sort of synthesized out of Sky Safari here. So the double cluster is beautiful in binoculars. It is beautiful in a very small telescope. A very high focal length, like an SCT, it looks okay. This is when you want to drag out your short tube 80 or your binoculars or your little tiny mini Dob. It's going to look a lot better in that. Each cluster is 1/2 degree in diameter, which I believe is about the size of the full moon. Someone correct me if I'm wrong on that. Both of these clusters are situated in what's called the Perseus OB1 association, right? So what this is, and I'm going to share a fascinating source on this at the end of the talk. So OB1 association, again, from an observer standpoint, I'm sure there are people in the room that could correct me on the science, but essentially this is these are large areas of stars that share some sort of common motion, suggesting they may have been created in the same place at some point in the past. They've split out into, you can think about them as like macro open clusters almost, right? I mean, giant open clusters of related stars. These are at a distance of about 7,000 light years, but only a few hundred light years apart. So this would look really cool if you were on a planet around one of these clusters, right? Half your sky would be dominated by one of this cluster. They're both pretty young, and we can tell this because they're so compact, but also the types of stars and that sort of thing that are in them. So they're about 5.6 or 3.2 million years old, depending on the cluster. To compare this, and you see they're very compact because they're fairly young. The Pleiades, which are much more diffuse, right, have an estimated age of about 75 to 150 million years, right? So double cluster, can't go wrong. Great viewing throughout much of the year. A question, so the Orion Nebula is out arm and not in the Orion Nebula. The Orion Nebula is in our arm in the opposite direction. So remember, we're on, so if you imagine that the arm is, I don't know, 6 inches wide, we're a quarter of an inch, half an inch in from the inside of the arm. The Orion Nebula is fairly close, but it's in the direction of the outer arm in that bulk. Same arm as us. Okay, our next object, again, we're still in the outer arm, the Perseus arm. But if you remember from, or if you have it up in Sky Safari, we're moving left to right across the sky. We're moving towards the edge of the Perseus arm. Okay, this is the OWL cluster or the ET cluster. This is also a fun one. It's 7,900 light years away, clearly in the other disk, or the other arm rather. So I don't know if you haven't seen this on your own, but if you see it, so it's upside down. It's been called like the Kachina doll cluster. There's lots of names for it. I prefer the ET cluster. It really does look like an alien to me. Looks fantastic in a very small scope. You do not need a large scope to see this by any means. So he's standing sort of on his head, a little cockeyed. These are his eyes. This is his body. His legs go down here. And his arms are out sort of like this. It's actually much clearer in a telescope from my driveway because you can't see all the background stars, right? So this guy stands out very, very clearly. Kids love it. What's cool about this, besides looking pretty cool, is that the brightest eye right here, Phi Cassiopeiae, is a foreground star located in our own local arm. How do we know it's in our local arm? It's only 2,300 light years away. So knowledge like this adds to that three-dimensional observing we can do, right? So we're seeing a foreground star with an actual cluster in the next star behind it. Again, one of my favorites. Now, if you remember that big map, we're moving over sort of towards Cepheus at this point. M52 is an open cluster somewhere between 3,900, 5,000 light years away. So that puts it outside of our arm, but not quite as far as these other objects were. So it might be sort of in the interarm space, or perhaps, on an outspur of one of these two arms. But you can see we're moving in the direction of that inner arm gap, right? So M52 was discovered by Messier in 1774. So one thing we can think about when we compare these clusters is the difference between visual magnitude, which is what we see, and absolute magnitude, which is the brightness the object would have if it were viewed from a distance of exactly 10 parsecs, which is 32.6 light years. So it's a way to standardize sort of how big and bright these clusters are. So this cluster's visual magnitude is 6.9, easily within the range of binoculars, but its absolute magnitude of -3.8. Okay, so if it weren't for all of the gas and dust in the way between us, it would be much brighter than it currently is, but a really pretty cluster. Okay, so we've moved into inner arm space, and we've jumped that inner arm space, and now we're looking towards Cygnus, down the length of our own Orion arm in the direction that we're traveling. Okay, so once again, we've crossed this space. We're looking this direction, straight down the arm. So we're going to get some very close objects, and we're going to get some very far away objects, depending on how far down that arm they are. Okay, so M39, I looked at this last night. I was waiting for that strawberry moon to come up over my neighbor's trees, and I had my short tube 80 out. Fantastic viewing, even with the moonlight. So get your small scope out and check these out. They're a lot of fun. M39 is only 800 light years away. Again, lots of background stars here. These images are all from the Deep Sky Survey. Again, the images from Sky Safari. It looks very much like an arrowhead in my eyepiece. Discovery is credited to Le Gentil in 1750. Messier added it to his catalog in 1764. There's some evidence that Aristotle may have seen it at some point. Visual magnitude of 4.59, but absolute magnitude of -2.98. Again, it's dimmed a lot by intervening dust and glass because it's by gas. It's pretty close to us. It should be much brighter than it is, but there's a lot of dust in the way. Looking down that arm. M29 is just a hop, skip, and a jump from our last cluster. I saw this also last night in my short tube 80. We're looking further. We're looking 6,000 light years. In this direction, that would put us square in the Perseus arm. In this direction, square in the Sagittarius arm. But we're able to look down our arm. Really pretty cluster. In my scope last night with very bad light pollution, it looked like a little box. The box was pretty much all I could see. Messier discovered this in 1764. Again, we're looking at a visual magnitude of I hope that's a dash, of 6.59, not -6. absolute magnitude of -4. Again, so fairly similar cluster to what we've seen before. This is part of the Cygnus OB1 association. So again, all these stars in this area of Cygnus are related at some point in the past. It's about 10 million years old and coming at us at 28 kilometers per second. Really pretty cluster as well. Okay, at 4,000 light years, our next object is NGC 6826, the Blinking Planetary. So this is the first of a couple, or three, I think three planetary nebulae we're going to see. So if you haven't seen this, this is a lot of fun too. So of course, a planetary nebula, as we know, has nothing to do with a planet, right? It's the remains of a sun-like star that's sort of puffed up its outer layers of gas. A larger star will nova or supernova, I guess supernova. But a star of the sun size will sort of just die this sort of pretty gas flowing death as it moves into dwarf stage. What's cool about this, and several of these, is that the differences between direct vision and averted vision, right? So if you look straight at the blinking planetary in a small scope, it disappears. If you look to the side with use averted vision, we have more rods that are sensitive to dim light in our peripheral vision. If you look to the side of it, it pops back. Look at it, disappears. You can do this all night and just make it blink in and out. If your scope is too big, it won't blink for you. So get that small scope. Like visit your friend with the small scope if you got the 20-inch Dob. I don't think it's going to blink for you at 20 inches. Other planetaries that have a really prominent central star also blink. For example, the Ring Nebula in my short tube 80 blinks, at least under my neighborhood skies. But the effect is much more pronounced with the Blinking Planetary. That one's a lot of fun, sort of up the wing of Cygnus. Right, we were up here. So we're going to move into this group of objects here. In Lyra, we're looking above the disk of the galaxy. Right here in Cygnus, we're looking again at the disk of the galaxy. Or down here in Sagittarius and Vulpecula, we're looking below, sort of below the local arm. And we can see this. This is a great piece of software too. I don't know if you played with it. It's called Our Galaxy. It's made by the people that make Sky Safari, or at least one of the developers. It's available for Mac. I'm not sure about PC, but the older version of this called Where is M13? I think that's what it's called. I think is available cross-platform, but check it out. So you're able to play with the galaxy in 3 dimensions. So what you can see here is that the Ring Nebula in Lyra, up here, no surprise to us, lies above the disk of the galaxy, right? Because we have to look up out of the galaxy to see it. The Angelfish Cluster, which is M71, I've never heard it called this before, but maybe it's a name that people know. I don't know. It's a globular cluster that is down and out of the galaxy, right? So we're looking down and out, and we can see that in this 3D view. So looking straight on, fairly close, at only 162 light years away, it's our neighbor. We have Epsilon Lyrae, the double-double, another fun one to spend some time on this summer. So you may have seen this many times already. The double-double, visible with your naked eye sometimes if your vision's good enough, but certainly in binoculars or a small scope. We see that that the star is a double star, right? You pump up the magnification or the aperture, and we see that each of those stars is actually a double as well. So the big double, right, is separated by 208 arc minutes. You can, again, some people can split that with their naked eye. These are much closer at about a little bit over 2 arc minutes, so almost 3 arc minutes. This is a really good test of seeing. If you can split the double-double pretty easily, it's probably a pretty decent seeing night. If not, might not be the night to count festoons on Jupiter. But again, this is a fun one, especially if you have a zoom eyepiece. You can start out wide and then zoom in and just watch those stars split, and you can sort of see where it is that you split. Is it a split at 16 millimeter night, or is it a split at 10 millimeter night? Okay, M57, the Ring Nebula at 1400 light years, also in our own arm. A perennial favorite. Discovered by de Pellepoix in 1779, who described it as, and I'm quoting here, a dull nebula, but perfectly outlined, as large as Jupiter and looks like a fading planet. That's become important. William Herschel later, who we know found Uranus, as along with the entire NGC catalog, essentially, thought that these objects looked a lot like those distant planets. And sure enough, if you've ever pulled Uranus up in your relatively small telescope, 6-incher, for example, it looks a lot like a planetary nebula in maybe a 4-inch scope. So Messier independently found this object while looking for comets and put it down into his catalog. Yeah, and so yes, so Herschel coining the term planetary nebula. Really, really fun one. This image matches what I see in about my, well, certainly what I see in about my 6-inch from Big Woods. The 10-inch shows a little more detail than this. In a really small scope, you're going to see it almost as a ball. You might get a little bit of the ring, but again, what can you see with the small scope, right? Can be a lot of fun. All right, M56, a globular cluster. Look at that distance, 31,000 light years. How in the world is that possible? How can we see something 31,000 light years away through all this dust and gas? And the answer, of course, is this is a glob. We're not looking through lots of dust and gas. We're looking up. We're looking out of the galaxy, right? So these are the Messier globulars, and we see as they form a halo around the galaxy. We can see globulars, for example, around the Andromeda galaxy, if your scope is big enough, forming a halo, right? So some of these, M3, for example, is way up there, right? Some of these are really far from where we are. We can also see that if we look at the open clusters, going back to open clusters, we saw this already with the image of the sky. Open clusters are located on or in the disk. You can see these globs floating sort of in the foreground, right? Open clusters in the disk of the galaxy, globulars outside the disk of the galaxy. M56 is a great glob. It was discovered by Messier in 1779. Herschel finally resolved it into stars in 1784. If you've ever seen a globular cluster in a very small scope, 80 millimeter, 4-inch, it looks like what I describe as the head of a Q-tip, right? It looks like just a little fuzzball. It's a faint fuzzy. So you certainly see why Messier would have been interested in these, right? They look a lot like a comet in a small scope. So 32,000 light years away, that gives its linear diameter of about 85 light years. If you haven't read it yet, there's a super interesting article in the July Sky and Telescope about the origin of globular clusters that I recommend you check out as you're thinking about these objects in the sky. Spring is galaxy season, summer is globular cluster season, right? We're able to position them above and below the galactic disk. Beta Cygni, or Albireo, one of the most famous double stars in the sky at only 430 light years away, neighbor to our sun right here. What's so cool about Albireo is even in the smallest scope, you're gonna separate this. It's 35 arc minutes of separation, easy to separate. But the color difference is what makes this so cool to look at and so pretty, right? We have this bright sort of amber or orangish Albireo A at magnitude 3.1, and then this really dark bluish, maybe sapphire-ish Albireo B at magnitude 5.1. We don't know for sure if they're actually a binary system. They could just be an optical binary. But if they are orbiting each other, it's a really long period, like 75,000 years or more. Lots of people call this the Cub Scout double because of the colors, right? The orange and blue. But this is a fun one to show people who, people tend to think that stars are sort of all the same color. And here you can show that, no, stars are very different color. And those colors tell us something about the age of the stars, the size of the stars, that sort of thing. Generally speaking, and again, I'm sure there are exceptions, but generally speaking, orangish red stars are going to be bigger and cooler. Blue stars are going to be smaller and hotter, right? Okay, we're now moving, if you remember that map, we're moving over towards the very sort of, I think that's the head of Cygnus, right? Albireo is like his head, flying with that long neck. And so we're getting close to this inter-arm space, but we're going to look at Brockie's cluster or the coat hanger at 4,200 light years. This is a fun one that looks horrible in a high focal length scope. In my C6, not even worth the time. In a wider field scope, if you can get a full couple of degrees of space, this looks a lot better. It's very obvious even in binoculars. So it's called the coat hanger. It's kind of upside down. You can see sort of the bottom there, and then I guess the hanger part. My son discovered this object when he was 5. He was scanning around with one of those little Celestron first scopes. He named it the speculus spatula. I don't know where the speculus part comes in, but yeah, I see the spatula part, right? It could be a flipper. What's cool about this cluster, besides just being fun to find, is that most of them, you'll notice, are hot, young blue stars. Whereas one of these stars, I think it's this guy right here, actually. One of these stars is an older red giant, although it's showing up as kind of yellow in here. But that's fun, too, to take a look at that and realize that you're looking at different age stars when you look at this cluster. Okay. Again, in our own arm, M27, the Dumbbell Nebula, one of my favorites as well. From the city, this image pretty much looks like what I see in a decent aperture telescope. So a 10-inch, 6-inch even. From a decently dark sky, I saw more detail than this in my short tube 80. So that was sort of the middle of Maine, no light pollution around. So this is really, really responsive to light pollution, if responsive is the right word. It's susceptible to light pollution. Under the right conditions, and this is why it's worth checking out, besides just the fact that it's cool looking. To me, anyway, it seems to float in front of the star field. It looks 3D. Of course, A, you're looking through one eye, right? And B, the parallaxes are so far away that we're not really seeing 3D, but that is certainly the illusion that's given. It looks really cool. M27 was the first planetary nebula discovered. This is, again, the outgassing of a dying star. Messier discovered it. And we believe we see it almost from the side, similar to M76 called the Little Dumbbell in Perseus. If we could rotate this object, right, so we're seeing it from the side, if we could rotate it this way, the idea is that there's a ring right here. So we believe that scientists believe that it would probably appear ring-shaped like M57. So again, you get that 3D view. We're seeing the ring nebula sort of from the top down. We're seeing the Dumbbell Nebula turned on its side. It's continuing to expand, although there's some uncertainty about how fast. It's probably somewhere between, if it's expanding really fast, then it's probably around 3,000 years old. If it's expanding really slowly, it's probably around 15,000 years old. So pretty wide range of error there. Yes, and Mike, thanks. Blue and gold for Cub Scouts. That's right. So looking down and out of our galaxy, M71, again, that this software calls the Angelfish Cluster. I don't know, you can put in the chat if you've ever heard that term. I never had before this software, but that's okay. At about 13,000 light years. So what's cool about this is that this was first seen in 1746 by an astronomer, a French astronomer named Deschazaux. And then later in 1780 by Pierre Michin. And so Pierre, of course, was Charles Messier's good buddy. They included it in the Messier catalog. For a long time, there was debate about what M71 was. Is it a very loose globular or a very tight open cluster? So there are some ways to sort of tease this apart. So globular clusters tend to be much older stars. And we say that because they don't, anything sort of metals, right? Anything sort of heavier than hydrogen or maybe helium, not a physicist, but it has to be produced inside of a star, right? So if you see a group of stars that are very poor in metals, very high in hydrogen, that's pretty much all they are, you guess they're probably pretty old and maybe aren't second or third generation stars. So most globular clusters don't show a lot of metal in them, right, in the stars. This particular cluster, however, has a higher concentration of metals than we would imagine, right? So that says maybe it's not a traditional globular. However, further analysis suggests that it's it's structured like a globular cluster, although probably a really young one. So again, there's that Sky and Telescope article on globs that may shed some light on this. They propose that globulars and open clusters may actually share a development. It may just be two sides of the same coin. So again, something cool to think about as we look at M71. Okay, we're moving across now that inter-arm space between the local arm and the Sagittarius arm, where there are relatively few objects that are going to be of interest to us. And again, right here, we looked at Cygnus. We got over here in towards Aquila. We're not seeing much. The tail of Aquila is going to produce some things again, right? So we're looking down that inter-arm gap. So once we jump that gap and we get into Scutum, we're going to see the objects pick back up again. I tend to think of the wild duck cluster as belonging to Aquila. I think it's technically in Scutum, But either way, it's clearly at the edge of this inner arm space here. So again, we've just taken our view from the left, from Perseus and Cassiopeia, across the gap to Cygnus, across the gap to Aquila, and now we're looking in towards the center of the galaxy. So here you can see this big jump. We now jump to 6,100 light years, and we're across the gap, so we know that it's not in our own arm. Okay? So our first object here is M11, the Wild Duck Cluster. It was first discovered by the German astronomer Gottfried Kirch, in 1681. Messier added it to his catalog about 100 years later. There was an astronomer, Admiral Smith, who noted that the cluster looked like a flight of wild ducks. I've never seen a flight of wild ducks, geese perhaps, so I'm not really sure, but it does look fan-shaped in a small telescope. It's so rich, in fact, that in a small scope, it's going to look a lot like a looser globular cluster, like an unresolved cluster. More aperture and magnification will crack it open into this really, really tight but brilliant cluster. They think it's about 250 million years old, so definitely worth checking out and not too hard to find. Okay, continuing our adventure on the Sagittarius arm, we have a group of open clusters that are all in the 5, 6, 7,000 light year range. So here's M26. I don't have a ton to say about this. It's really pretty. As you move towards Scutum and Sagittarius, it can take some experience to spot these open clusters, because they're not like the Pleiades just hanging out on their own, right? They are essentially, especially in a small scope, concentrated pieces of the background star field. So in some ways, these clusters can be easier to see in less dark skies, because you're not having to deal with the background stars. Also, if you're in a small scope, like in my short tube 80, a lot of these open clusters just look hazy. They look like a hazy spot. And that haze tells you you're looking at either nebula or unresolved stars. And in this case, we're looking at unresolved stars. Remember that Messier, at least initially, started out looking for false comets, right? Later on, he added objects because he wanted a nice round number or whatever it might be. But early on, in a very small telescope, a lot of these objects look very comet or nebular-like. Visual magnitude is 8, apparent magnitude of -3. So again, it's being dimmed by a lot of gas and dust. Okay, so as we move out of Scutum, we move to the Sagittarius Southern Scorpius. And again, the order I'm doing this in is the order that if I'm got a couple hours to kill on a weekend night at Big Woods or in my driveway, I start in the north and sweep in this direction, right? It's sort of my go-to sweep. You'll get to the point where you don't even have to look at the star chart that much. You know what your next object is. You know about where it is, especially with a wide field scope. So again, we're looking across the void into the center of the galaxy. I'm also going to go out of order here. I've tended to sort of sweep in this direction, but once I get to Sagittarius, for some reason, I jump down here to the tail of the scorpion and work my way back up. I do this just out of habit, but also because you can stand, for example, at Big Woods, and you can do this with your naked eye. There were 3 or 4 of us out one night, late one night, people were starting to pack up, and we sat there and did it. We're like, who sees the Ptolemy cluster? Yep, got it. Who sees the Lagoon Nebula? No problem. Who sees the Trifid? Not so sure. Oh no, I think I got it. I think I don't, right? And you can work your way up. A lot of this stuff over here from moderately dark skies is naked eye visible. So again, we're facing in this direction now, straight across the void into the next arm. Note that the arm past it and the center of the galaxy is essentially blocked by the dust and the gas of the Sagittarius arm, just like we can't see out to the Perseus arm past the dust and gas in our own local arm, except through that window near Perseus and Cassiopeia. But we'll look at some windows in a minute that will allow us to see more. So again, I'm going a little out of order into the order that I normally sweep out of. So we're dropping down to the tail of the scorpion, to M7 Ptolemy's cluster. This is 980 light years away, which tells us this is a foreground object. This is not in the Sagittarius arm. It is in our own local arm between us and the Sagittarius arm. This image doesn't actually do it justice. If you've ever seen this in a small scope, it is beautiful. It's breathtaking. Again, it's a naked eye object. It was known to Ptolemy. There are a lot of theories that a lot of ancient cultures attributed this to be the poison from the sting of the scorpion, right? It was observed originally in 1654 by Hodierna, an Italian astronomer. Halley listed it as well in 1678. Lecoq added to his objects. Messier finally tacked it on in 1674. Looks much better in a wide field scope or telescope or binoculars. Looks much better, for example, my short tube 80 than my C6. I haven't gotten my relatively new Dob on it yet because it won't stop raining, but hopefully soon. Its visual magnitude is 3.29. Its apparent magnitude is -4.1. We'll compare that to its neighbor M6 in just a moment. So M6 at 1600 light years, a foreground object, but really sort of at the very edge of our local arm, right? Or maybe something hanging out in that inner arm space. That space, just like, you know, our solar system isn't empty. It's just not highly concentrated. So this is almost twice as far away as M7, okay? So if you've seen both of these, M6 is much smaller and tighter and more concentrated than M7 is, right below it. And that has to do with both its distance, it's almost twice the distance of the Ptolemy cluster, but also its size, right? It's also, it is almost twice the distance, but the same apparent magnitude, -4.25. So these clusters actually are really, really similar. Sorry, thinking about some clusters we're going to talk about in a minute. These clusters are actually very, very similar. One is just further away, so it looks smaller and tighter to us. Again, that gives us that 3D view of the galaxy, right? Robert Burnham, in his 3-book volume set, speculated that this was also seen naked eye by Ptolemy. I believe it. I think I've seen it naked eye from decently dark skies. Again, it just looks like a hazy patch, right? This is, right, so it was independently then rediscovered by Deschazaux. Messier finally added it in 1764. This is called the butterfly cluster because in a smaller scope, without all the background stars, it really does look kind of like a butterfly. This is the body, and the wings come out this direction. Hopefully you can see my cursor here. Again, not so much in this image, but in the eyepiece it does. Cool trivia point, the butterfly cluster is the closest M object to the direction of the center of the galaxy. Not to the center of the galaxy, to the direction of the exact, was it Sagittarius A, the direct center of the galaxy. So look at the butterfly cluster, you're looking almost dead on. Okay, we're jumping back out to the arm and we're working our way up that teapot, right? If you have it open in Sky Safari, you can just imagine this, we're working our way up the teapot to M8, the Lagoon Nebula, 4,300 light years away. So the Lagoon Nebula took a while for me to appreciate it. People sort of described it as the summer Orion Nebula. And if you've observed both of these, you know that's not true, actually. The Orion Nebula slaps you in the face with this really cool nebulosity and these bright stars. First couple times you look at the Lagoon Nebula, especially from a light polluted area, and you go, yeah, I maybe see a little glow there. It's more subtle than it appears in this image. However, I've come to really appreciate it. What's really interesting about the Lagoon Nebula is it's very easy to pick out in binoculars. You can see that glow clear as day. But what you're seeing, I think, is not maybe, you're seeing the glow of the nebula combined with the glow of the unresolved cluster, right? So it gives it this real hazy view. But in a bigger telescope, a filter really helps. This really responds well to one of those, what are they called, UHC filters? I think that's what they're called. So I have this Orion filter that really makes it pop. But in darker skies, you see it really well. Like the Orion Nebula, it is an area of new star formation. The lagoon is dark material or a dark nebula that divides the nebulosity in two. It's really cool when you think about, you have different types of nebulae, and one of them is a dark nebula. Like, well, how in the world can I see a dark nebula? And it's a place where you don't see any stars, right? That's a dark nebula. There's some debate about whether or not Messier saw just the cluster or saw the cluster and the nebula as well, but some descriptions suggest he saw both of them. So again, this is a showpiece object, but you can see it in a really cool way in a very, very small aperture. In a bigger aperture, to really pull that nebula out. A filter can really, really help. So M20, the Trifecta Nebula, in a wide field scope in the same field of view with the Lagoon Nebula, but just, I don't know, a degree and a half up. Again, at 5,200 light years in the next arm, in the Sagittarius arm. So in a small scope, you may only see the cluster, which is NGC 6514. You may not actually see the nebula at all. Although I was able to see the nebula with the division from my C6 at Big Woods. So it's not that hard to crack. It's a pretty rare combination of an open cluster combined with an emission nebula that's producing its own light, a reflection nebula that's reflecting light from other stars, and a dark nebula that divides it into 3 parts, hence the name, the Trifid, right? And again, the emission part of this is an area of star formation like M8. Some other cool trivia. Sky Safari notes that images of the Trifid Nebula often appeared on the set of the Starship Enterprise in the original Star Trek television series. I haven't had a chance to go back and watch all 3 years of that, but keep an eye out next time you're watching Star Trek. You might see the Trifid Nebula up above Mr. Spock. Really fun one to look at. We're going to look now at a series of open clusters in the next arm in. And the fact that we can see open clusters at a distance of 3,900 light years in the direction of the center of the galaxy lets us know that we're on the inner edge of this arm, because we're not looking through a ton of dust. We don't see any open clusters this direction outside of our arm, right, that are this far away. And then B, that we're looking across sort of the lack of intervening material, relatively speaking. It's a really pretty cluster. These are just, all these clusters look great again because they're backdropped by the Milky Way. This is an apparent magnitude of -4.5, very similar to Ptolemy and Butterfly's clusters. Again, getting a feel for, right, this one's much further away, but a similar apparent magnitude. So very similar clusters, even though we see them very, very differently due to distance. M23, another open cluster at 2,000 light years. It's the size of the full moon. It was discovered by Messier in 1764. Again, another cluster. It looks great. So this is, you're barely nudging the telescope, right? Or if you're using GoTo, you'll punch in GoTo and it will like, and you're there. Because these things are all within a degree or two of each other. Visual magnitude of 5.5, apparent magnitude of -3.49. So a little bit less intrinsically bright than some of the other ones we've seen. M25, another open cluster. Again, at 2,000 light years, probably on the outer edge of the inner arm, right? It's too far away to be in our own arm, but it's not fully embedded like some of those nebulae were. Again, pretty cluster. So this one has some cool trivia to it. It was discovered by Deschazaux in 1746, reobserved by Messier in 1764. Lots of Deschazaux's observations, either they were lost or they weren't published until later. So lots of these things that Messier discovered were actually pre-discovered by Deschazaux and just lost for a period of time. For some reason, William Herschel did not include M25 in his catalog. And as you may know, his catalog became the NGC, the New General Catalog. So this is one of the very few items, and as far as I know, the only Messier item, someone correct me if I'm wrong, that doesn't have an NGC number. It has an index catalog number, an IC number, and of course the Messier number. Its visual magnitude is 4.5, apparent magnitude of -4.37, inherently similar to the other clusters we've seen. But again, we're seeing how distance and intervening gas can have to do with what we see in the eyepiece. Okay, now we're going to take a huge jump for a moment, and we're going to look at the small Sagittarius star cloud M24, one of those windows into the inner arm. Okay, we're looking 12,000 to 16,000 light years away here. So what we need to, it's essentially a bright spot in the Milky Way. It's a section of a far interior arm, probably the Norma spiral arm. Sometimes you'll see different names for it. What's cool about this is there's about a 600 light year wide window in the dust and gas of the Sagittarius arm. So the Lagoon Nebula, the Trifid Nebula, the Omega Nebula, all of those star clusters are all in the Sagittarius arm. And it's like someone has pulled back that dust and allowed us to catch this little glimpse straight through to the next arm in the galaxy. These windows are really important because without them, our view would be blocked and it'd be very, very difficult for us to understand and appreciate galactic structure because we'd only be able to see those three particular arms and probably only mostly our own arm. You remember, if you go in the direction of Orion, we can't really see the Perseus arm. It's blocked by our own arm. We'll come back to this window in a moment, but we've jumped an arm there through one of those windows. Just a couple more objects and we'll wrap this up. So M17, the Omega Nebula or the Swan Nebula is again a perennial favorite. In the next arm at a distance of 4,100 light years. It's visible to the naked eye under good conditions from a semi-dark site. I've seen it naked eye from big woods. Again, just as a glow, right? Again, first discovered by Chazot, rediscovered by Messier in the same year. Like a lot of the nebulae we've seen, this is new star formation taking place. For me, when I see it, so this is it's the Omega or the Swan Nebula, right? So if you imagine the swan is upside down, so this is water, this is his body floating on the water, here's his neck coming around, right? That's the idea. From my scopes from my driveway, I don't really see the head. I see a check mark, right? It looks like a check mark to me, a lot of ways. It also has, and I don't know if anyone else, you can mention this during the questions if you want, or put it in the chat. To me, the Omega Nebula or the Swan Nebula and the Dumbbell Nebula have like a reddish or almost brown tint to my eyes. Most of the other nebulae and stuff look sort of grayish to me. Sometimes I'll see hints of green in the Lagoon or in Orion, just very small hints of it. But these look reddish or brown to me. And what that does is, for me, it pulls it out of the star field and makes it appear like it's floating in front of the stars. Go check this out on the next clear night and see if you see that effect of it floating for you. It's pretty cool. Jumping up, we jump to the Eagle Nebula at 5,700 light years away in Serpens. As with the Trifid, in a small telescope, you may only see the cluster. For example, even the Herschels with their giant, massive telescopes didn't see the nebula. That said, the nebula is not that difficult with a modern scope of, say, 6 inches or so. Messier describes it as stars enmeshed in a faint glow, right? So he apparently saw the nebula. That describes pretty much what I see. Again, it's another star-forming region on the inner Sagittarius arm. This particular thing was made famous by the Pillars of Creation Hubble photo, right? And so, yeah, Doug points out everyone sees color in a slightly different manner. We did a thing with Phyllis Lang a couple of years ago during the summer. We all tried to see if stars looked green to us. And they did to some people and they didn't to others. It was really cool to take a look at that. So this is what made the Eagle Nebula famous, the Pillars of Creation. Now, you ain't going to see this through your short tube 80. From Big Woods. But I think Mike, correct me if I'm wrong here, but we pulled it up one night on your EAA setup and we actually could see this. I'm pretty sure. It's tiny, but it's there.
Oh yeah.
Is that right? Yeah. Yeah.
That is true.
So check it out in EAA, but just know what you're looking at, which is really cool. Now, real quickly, I want to jump down to Sagittarius and look at a few globular clusters. And I'm not going to say much about most of these, but we can really tell distances here, which is really cool. So M22 is one of my all-time favorite globular clusters. It's super easy to find right here off the top of the teapot. And again, these globulars are below the disk, right? We're looking down from the disk. M22 is relatively close, relatively. M54, for example, is all the way out here. So we're going to focus on comparing those two. M22 is about 10,000 light years away, one of the nearest globular clusters, one of the first to be discovered, the third brightest globular cluster, only 47 Tucanae, which you'll never see from Raleigh, and Omega Centauri, which you'll see from Raleigh during about a 6-week period if you have a super clear south horizon. Even my smallest scopes start to resolve this into stars. Beautiful, beautiful globular cluster. So it is, keep that in mind, third brightest globular cluster that we can see in the sky, 10,000 light years away. If we compare M28 just on the other side of the teapot, Yeah, super, super easy to find. If we compare M28, this is one of those clusters that would be a showpiece if it weren't so close to M22. Comparing these two gives us a good idea of distance and size. So M22 is about 97 light years across at about 10,000 light years away. M28 is almost twice as far and about 2/3 of the size, about 72 light years. So what we see then is that this globular looks much smaller and dimmer to us because it's farther away and smaller. However, when we drop to the bottom of the teapot, there are 3 small Messier globulars that are a pretty good challenge in a small telescope, both due to their size. They're pretty tiny. This is one of those things that you expect it to look like M22, and it looks nothing like M22. It looks like an out of focus star at first. So due to the fact that they're small, but also the fact they never get that high from our latitude, right? They're much easier probably from the equator. But this is, remember that M54 that was way out there. M54 is 3 times as large as M22. It's 300 light years in diameter. But it's also 9 times further away at 86,000 light years. If it were as close as M22, the 3rd brightest glob in the galaxy, it would be an easy naked eye object, bigger than the full moon. That'd be pretty cool to see. M70 and M69 are both about the same distance, 29,000 light years, and both about the same size. And they look almost identical. So that's a case where they're identical because they really are almost identical. But this comparison between M54 and M22 really shows you how much further out M54 is. It's massive compared to the 3rd largest globular cluster that we can see. Okay, to wrap up, this is the last, we're going to peel back that onion, right? As we're looking at these objects, and again, you can sort of star hop them this way. Remember that when we look at the Milky Way and we see the Great Rift and we see these areas, what we're seeing is areas of dust and gas, a dust lane, with areas poking through that dust lane, essentially, right? So again, this is what we see in the visual spectrum, right? And the center of our galaxy, the bulge, is hidden largely by dust and gas, intervening in our arm a little bit, in the Sagittarius arm, in the Norma arm, etc. But if we look at the Milky Way, and this is right from Sky Safari, if you look at the Milky Way, for example, in infrared or an X-ray or in something else, we can bust through that dust and gas. And we can begin to see part of the bulge. I think it's even bigger than this, actually. We can see part of the bulge here in infrared. And so look at this little corner right here as I go back and forth, right? Most of it's hidden to us. These little 3 stars right here, this little corner. Oh, I went too far. That's a little corner of the bulge that is visible to us through another window in the dust and gas. So we're going to peel back this onion. Looking towards Sagittarius, we can see at least 4 layers of galactic structure, okay, that we can peel back one at a time. The first layer are the foreground stars and clusters in the local arm. These are between 70 and 2,000 light years. Basically, every star you see in here that's not part of a cluster is foreground. All of these bright stars in Sagittarius, the Ptolemy cluster, the butterfly cluster, all of Scorpius, that's all foreground, right? So that's layer number 1. We then jump from 2,000 light years to 5,000 to 7,000 light years. We jump across that inner arm gap to the next layer, which is the clusters and nebulae in the Sagittarius arm. This includes the Lagoon Nebula, the Trifecta Nebula, the Omega and the Eagle Nebula, which are further up here, not the star cloud, sorry, the Omega Nebula and the Eagle Nebula, and these other open clusters that are here, right, along the galactic disk in the next arm. So now to see further than that next arm, remember, looking towards Orion, we can't see any further. To see further than the next arm, we need to use the windows. And that one window, as we mentioned, is the Sagittarius Star, the small Sagittarius Star cloud. There we jump to about 16,000 light years away. We're peering through the local arm, through the Sagittarius arm, to the inner arm, probably the Scutum Centaurus arm or the Norma arm, depending on the name. These objects are at least twice as far away as these other nebulae are. Again, imagine someone pulling back the curtain. Finally, we have layer number 4, which is the large Sagittarius star cloud, which is this piece of the bulge right here, at least 30,000 light years away, just above the teapot. So remember back to those infrared versus visual images, right? We see that most of the bulge is hidden by this dust and gas, but a little corner peeks out. We believe the center of the galaxy contains a supermassive black hole, about 4 million solar masses or more. There's probably updated information on that. A very high density of stars. So near the galactic center, the average distance between stars would be about 1,000 AU. That's only 1 light week. So what that means is if we were located nearer to the galactic center, there'd be 1 million stars in our sky brighter than Sirius. The total starlight would be 200 times greater than the light of the full moon, bright enough to read at midnight. Now, while that would be cool to think about and look up and see all those bright stars, we're really lucky that we're not situated there, because we would not be able to discover hardly anything about the rest of the galaxy, at least not in visual light, because we couldn't see past all these stars. And you have to wonder, open philosophical question, would we have even developed microwave and X-ray telescopes and whatever else we have if we weren't first inspired by these questions from visual astronomy? So I'm just going to close with this quote. I think it sort of wraps up what we see here. On the surface, just a fun list of 30 objects to look for in the night sky during the summer. At a deeper level, helps you to feel connected to where we fit in the scheme of things. So again, this is the QR code to download these files. You can download it as a spreadsheet or as a Sky Safari file. I'll put the link back in the chat as well. I'll come back to that. Just a couple of sources. Sky Safari 6 Pro on the iPhone and Mac, I use for star charts, object info, DSS images, overhead galaxy view, and then the Our Galaxy app for 3D galaxy views. And then some books I can recommend. There's a lot of stuff out there. And again, it's being updated all the time. That binocular astronomy book, once the price comes back down to $10, well worth it. The Guide to the Galaxy, another great book from 1994 that talks about the different arms. Again, a lot of the scientific details are going to be outdated. But if you view it from an observer's perspective, that's still legit, right? And thinking about how we frame things. I can't not mention Turn Left at Orion. As I was making this list to observe, I went back through and reread Turn Left at Orion just for something fun to do, and realized that I had inadvertently recreated a large portion of their summer list, right? These are just the top objects. It was the first astronomy book I had, and I still take it out sometimes if I'm looking for something to find. If you're on cloudy nights, Google the Classic Rich Field thread. This is by a Danish astronomer named Alan Dijstrup. This guy goes out in his Copenhagen backyard and looks at all of these large structure objects through small classic refractors, essentially. And he has this whole thread, it's dozens and dozens of pages talking about OB associations and talking about how we can relate to these things. Fascinating read, definitely check that out. And then Matt Weddell's blog, 10 Minute Astronomy. It's not updated that often now that he is doing the binocular astronomy column in Sky and Telescope, but he has several posts that talk about these different ways of seeing the cosmos as well. So I hope you enjoyed the talk. I hope you can get out sometime on Stop Raining and check out these objects. Thanks. I'm happy to take any questions.
If everybody wants to go ahead and unmute and just ask. We've got
There's that link again.
Group.
Well, thank you, Jim. So anyone last questions? This is a great talk, I thought.
It's fantastic. Can you would you be willing to upload the slides to your Google Drive?
Yeah, sure, no problem.
That'd be awesome.
So fantastic talk, Jim. That was awesome. I will say that, and to echo some of your recommendations, Turn Left at Orion, the most recent printing of that, I think they updated it in 2018, and there was one that was even printed in 2020, I think. Yeah,
I've got like the 2000 version, but it's I think it's spiral bound now, which is nice.
Yeah. Hold on. You can't really see.
No, I know you can't on mine either, but fantastic book.
Yeah, no, absolutely.
Here's the thing too, is that people will often, you hear all the time that like, oh, I wish I had a bigger scope so I could see these objects. If you remember, someone shared a link a while back. There was a talk from like Michigan or somewhere with Guy Consolmagno. So one of the authors of this, right? And his telescope was sitting in the back. So this was done with a C90, right? One of those old school little 90 Max. So you can see a ton of stuff. You got to think about it as fly fishing versus deep sea fishing, right? You ain't deep sea fishing with the short tube 80. You're fly fishing, and you're seeing what you can catch along the way.
Yeah.
Sorry, Mike.
In the newer one, they go through and they try and provide multiple views through, kind of like 8-inch Dob, small scope. So anyone just starting out, this is a phenomenal reference that would just really, really help out. So fantastic. Just want to also note that while you were talking, I downloaded our Galaxy. It is free on iOS. So that is really cool. Thank you.
Yeah, that's a really cool app.
Yeah.
I found it when I was looking for, I think the previous version was called Where is M13, and it might still be out there. But this one, you can zoom in. It's really cool. 3D Galaxy View software for Windows. I don't know. I'm a Mac guy, so I'm not sure. It may be available for Mac for all I know. I found it on the App Store, but that doesn't mean, or sorry, for Windows. That doesn't mean it's not out there. It's by the people that do Sky Safari, so it wouldn't surprise me. Although I think it's a side project, like it's free.
Yeah. Yeah, which I would imagine. I mean, Sky Safari is pretty much Mac or iOS or
iOS. Yeah. Well, and I suspect that some of this may be implemented in the Galaxy View in Sky Safari at some point. Robert, there has to be software out there. I'm just not sure.
Yeah, Carte de Seal is that's Windows, and I think Stellarium.
Yeah, I don't know if you can 3D Galaxy on that though. What was the other one I was thinking about just a minute ago? Celestia. You guys use that? I played around with it a little bit. It's a little intimidating at first, but yeah, I think might be available cross-platform, and it's a way to sort of you can like orbit, Alpha Centauri and see what it would look like, sort of thing.
Carte de Seal has the most like catalogs I've ever seen.
Yeah,
you can download dozens and dozens of catalogs for it.
Okay, and Stellarium Plus on iOS. Stellarium was even available on iOS.
Huh, okay, so it's fine. Jim, when you were doing, I think some of those views through Sky Safari, it looked like you were adding observing lists and able to denote that. Was that through the Mac or iOS, or is there a particular feature?
Yeah, I did this on the Mac. So you're talking about like these images?
Yeah, in fact, I think it was even one of your first ones where, and I guess actually that could be too, but yeah.
So like just sort of like when I give the overview.
Yeah, yeah, I think that was. Yeah, it probably was.
Yeah. So on.
Okay. Yeah. Yeah.
Right. So on, I guess you could screenshot it on iOS, but on the Mac, you can export the star chart, and it's going to export whatever as like a JPEG.
Yeah, because I think you had one where it showed, all the globular clusters or open clusters.
So all of the AL, right? So I just went on the Sky Safari on the Mac and just downloaded the AL open cluster list, and then just showed it, to show where you can view the objects.
Okay.
And then just exported it.
Cool.
Yeah, like that one right there.
Yes.
That award's going to take a while.
Okay. Are there any other questions?
I will make a comment on M16 the Eagle Nebula. That is one where, and I don't know if anyone else has had experience. I know when I tried using just the standard UHC filter, even in an 8-inch, I couldn't get the nebulosity to pop. But most of the other items or the other objects you mentioned with some nebulosity, with just a standard UHC, they seem to do well with the filter. I don't know if you have to use O2.
do. If you use too good of a filter, the Blinking Planetary loses its fun because it stops blinking. No, the Dumbbell looks great in a UHC. The Lagoon Nebula looks great in a UHC. The Trifecta Nebula. I agree. What's cool about that sort of that jump, working your way up here again, is that you can see where these objects are naked eye. Again, what you're seeing is mostly cluster, right? And in binoculars, it looks great, and you're like, oh, I saw the nebula, and then you put your 8-inch on it, and it's not there, and you go, how is that possible? But these things look really, really cool in binoculars as well. The things that aren't going to look good in binoculars are some of the globulars. But to be honest, most and some in the planetaries aren't going to look great. But other than that, these things are going to look pretty cool. I mean, they're going to look different, right? But they're going to look pretty cool in binoculars.
Yeah. Coat hanger is horrible in a telescope.
Horrible. 280 the other night was fantastic.
Yeah.
Yeah. No, horrible in like my C6.
Or look at it through your finder scope.
Look, that's exactly right. Yeah, and I think somebody posted, forget who it was, Caroline, that she saw the coat hanger the other night. So at RAC, it was very cool. The specula spatula, as we call it around my.
I will say, while I was looking, I posted a link earlier on in the chat. There is that book, Binocular Astronomy. It is available in the $30 range through some other used book.
Oh, cool. Awesome.
Outlets. So I posted that in the chat.
Yeah, no, I mean, you can go into Cloud Nights and investigate this. There's the rumor is that the second edition was published without the author's permission, and they received no royalties. So that's the rumor. So if you can get a first edition or investigate that on your own, but I think because the second edition to Crossan's book is actually called something else. It's called something Skies. I'm gonna have to Google that, or somebody can Google that real quick.
Sky Vistas, I think.
Sorry, what is it?
Sky Vistas.
Sky Vistas. That's his follow-up book. That's right.
Yeah.
That's right. That's also a cool book because it talks a lot about the mythology. And not just the Greek mythology, but like the fact that a lot of these, in particular the zodiac constellations or like Hercules and stuff like that are really, really ancient. They show up in and pottery and that sort of thing. It's pretty cool.
So Jim, what prompted you to kind of put together this? I mean, 'cause obviously you had to do some work and find the distances and try and figure the geometry of that out, which was amazing. Thank you. But kind of what prompted you to do that?
So I mean, it really was that I'm trying to take that next step into sort of understanding where we are, and the fact that to be honest, once I found out through reading a lot of these sources that you could actually observe this once you understood just a little bit about distances, or I mean, because I would, like I said, when I would never have noticed the fact that there's nothing to look at in Aquila. I'm cruising the Milky Way and I'm like, oh, now next object is the Wild Duck Cluster. And so and of course there are things in Aquila, right? But not sort of your showpieces, at least not in this part of Aquila. So I just really wanted to just understand where we are in and add that dimension to my own observing. This particular observing list, I mean, I put it together for this talk, but this observing list is my go-to summer observing list. I don't know what else to do.
Oh, okay.
I'm going to start at one end of the Milky Way and cruise my way there. And if you're just cruising along the whole way, if you're using go-to, you're going to jump, of course. But if you're cruising with your small scope, you're going to run into clusters that you don't even know what they are. They're all NGC somethings. You can see they're all those, right? But just a really cool way to spend a summer night. And so I think it was that, Mike. It was the fact that the revelation that you can actually see this yourself was just mind-blowing.
Yeah.
Oh, yeah.
So I think there was a question earlier on in the talk about Orion. So someone asked, so the Orion Nebula is out of the Orion arm.
No, right. So the Orion Nebula is in our arm. So, right. So this can be confusing. This is just the direction that these constellations. So when you're looking towards Sagittarius, you're looking inward on the galaxy. You're looking towards Cygnus, you're looking up the arm. When you're looking towards Perseus or Cassiopeia, you're looking, or Auriga or Orion and Gemini, you're looking out. But the trick here is that there's that window in the dust and gas in this direction that doesn't exist in this direction. So we're able to sort of peer through a hole in our own arm to see the objects out here. But if you look towards Orion, the Orion Nebula is actually really close, relatively speaking, to the sun, right?
1,500 light years or something.
Yeah, it's right nearby, which does make the Lagoon Nebula that much more impressive when you realize how much further away that thing is, right? How cool that would be to have it 800 light years away. So the Orion Nebula is somewhere around in here, but because we're looking through the bulk of our arm, we don't see any of this arm or very little of this arm past that direction, right? So if you're looking out in that direction, you're only seeing our local arm. So the Orion Nebula is right there in that Orion arm, or spur, or whatever you want to call it.
Yep.
Okay.